Hi everybody, narrated solution number 1. Consider the region bounded by y equals 4 minus x squared, y equals 0, x equals 0 for x is greater than or equal to 0. Revolve the region about the x-axis. So the first thing you're always going to want to do when you solve problems like this is to draw a picture. So pause the video, recreate the picture that I have drawn above, and we'll meet back in 2 seconds. Pause. Hello. Okay, so the first thing you're going to always want to draw is the function. What does the function look like in the coordinate plane, bound it between the appropriate region, and then sketch your little representative rectangle, because this helps us envision the 3D solid we would get if we rotated the function about an axis of revolution over a bounded area. So we have our 3D shape, and then we slice that solid to generate a disk. And the disk would look just like this, with radius f of xi and delta x as the thickness or height of the disk. So first, let's approximate the volume of that disk or increment of volume denoted delta vi, that's increment of volume. So the disk is simply a cylinder, so we will find its volume by multiplying pi times the disk's radius, and then we're going to square that, because remember, in volume of a cylinder, it's pi r squared times height, so think about that. Then we will multiply it by the height or the thickness, if you laid the cylinder flat, right, of the disk. So this is our radius, and then this is our height or thickness of the disk. Okay, so that is an approximation of the increment of volume that we will be using to approximate the solid's volume. So the approximating Riemann sum that adds up these super skinny disks, or increments of volume, is going to look like this. We have the approximate volume when I starts at 1 and ends at n disks, and it would look like this. Now, why is this an approximation? Because a Riemann sum has discrete inputs, right? You are starting at 1 and going all the way up to where n is, whatever n is going to be. So this is going to be a discrete approximation, therefore it's an approximation. But when we turn it into a continuous or an integral, we would let n in the Riemann sum, approach infinity, and that will obtain the definite integral that will give us the exact volume of the solid. So now we have our exact integral. Why did it stop? Oh, it's still going. Sorry. So that will give us our exact volume, and it will look something like this. Volume is equal to pi. I factored the pi out because whenever I'm dealing with integrals, it's always easier to just factor out the constants, deal with them at the end, right? So 4 minus x squared, if I expanded that, that's going to give me a polynomial, and that's going to make it a little easier to integrate. So that's just me expanding out the 4 minus x squared from up here, okay? And then I've got my dx out here because now it's an integral. Notice how when we go from Riemann sum to integral, that delta x changes to a dx, right? The delta x is talking about discrete inputs, and now the dx is talking about continuously summing this area. So now we would calculate by integrating, and we would evaluate at our higher bound minus lower bound. You all know how to integrate something like this at this point, so I'm just going to save us the time, give you the answer, and see if you can generate this on your own.